Okay, so welcome everybody to the next installment of our calculus class this semester. And it's been 2 weeks, so may have forgotten some things from the last time, but we'll be able to go over the homework. And we're starting a new unit today, so it should be pretty, it's okay if you haven't followed everything completely coming up to now. So yeah, I hope everybody is doing fine. I was saying for the people who just came in, I have not slept so well this week. You may notice my voice is a little lower and a little slower than usual, but hopefully that's fine for comprehension and I don't put any of you to sleep. So okay, great. So I want to talk about limits today. That's going to be the main topic. But before we get to that, we should go over the homework. So by the way, if you do the homework exercises, please send your solutions either just to the full group on WhatsApp, or you can send it privately to me on WhatsApp, or you can send it to me by email. However you want to do it. It's good to, that I have a record that you're doing the exercises, and also if there's any mistakes, then I can point them out and it can be useful for learning. Okay. So let's start, I guess, by going over. Oh, and also please, yeah, type your name into the chat if you haven't done it since I started recording, then please do it. If you type the name before I started recording, then it's not going to get saved. So please, if you did it before, please just do it again so that I have a record. It only records the record after I start the recording, which was 2 minutes ago. Okay. All right, so let's talk about this first exercise, which seems like it doesn't have anything to do with calculus, but actually it has a lot to do with calculus. And basically, one of the morals of the story for this semester is calculus, linear functions are the most important thing in all of calculus, right? It may seem like they're the simplest thing, but they're actually the most important thing. Okay, so let's look at this exercise. So the manager of a furniture factory finds that it costs $2,200 to manufacture 100 chairs in a day, and it costs $4,800 to manufacture 300 chairs in a day. So that's for 100 chairs. This is for 300 chairs. So assuming that the cost, I'm underlining these key words, is a linear function of the number of chairs, express the cost as a function of the number of chairs. And the hint is, can you start by figuring out the slope of what this function is? So let's just recall, even before we start solving this, let's just recall what a linear function is. Linear function is given in the form f of x equals mx plus b, where what's going to be important for us, this m over here is the slope. Okay. So this m over here is the slope. So we want to figure out what is the linear function that models this production process, right? And so what we know, what we're given, is that if f of x is going to be this linear function, what we want to think about, we're trying to express the cost as a function of the number of chairs. So the inputs are the numbers of chairs, and the output is the cost. So what that means in terms of math is that f of 100 is equal to 2,200, and f of 300 is equal to 4,800, right? These numbers here, these are the inputs, right? Because it's a function of the number of chairs. And the cost over here, that's the output. That's the result of the function. So if we want to figure out what linear function this is, another way of thinking about this is graphically. We want to say if I have a function that passes through these 2 points, 100, 300, I'll have my graphs at a different scale. So 2,200 and 4,800. Then I want to know what is the line that passes through these 2 points. Right, so these are my 2 points that I'm giving you. I know that there's a line that passes through these 2 points, and I need to know what line that is. So how do we figure out that line? And so the hint is, first, can we start by figuring out the slope of the line? So how would we figure out the slope here?
Hello?
Hello, yes?
Yeah, to figure out
James?
the slope, you got a formula, the rise or the run. Or
Right. Hmm.
you got y2 minus y1 or x2 minus x1.
Great.
So if you use that formula, you will have the first number for the y2 is the second number, but you have
Hmm.
480,
Hmm.
4,800 minus 2,200 divided
Hmm.
by 300 minus 100.
Hmm. Great.
So if you do that, you like do your subtraction, you get a fucking divide. That'll be your slope.
Right. And so what do we get for the final answer for the slope here? So we get
13.
2600 over 200, and that's
13.
13. Great. Okay. So that's our slope. Our slope is 13. And so we know that that means m is going to be 13. So we know that the linear function we want is going to be f of x equals 13x plus something. Okay, and so the question is, how do we figure out now the b? So we now get that what we want. So the function is y equals 13x plus b. All right, so how do we figure out what b is? Any ideas how we figure out what this other thing is? Well, maybe I shouldn't, by the way, I shouldn't say
Yeah.
y. I should really say f of x. F of x is equal to this. Okay, yes. Somebody was going to
Yeah,
answer?
that's
Hmm.
it.
Yeah, Abraham.
What you have y,
Hmm.
that's a y minus 13x is equal to b.
Hmm. Right. So y minus 13x is equal to b. And so then what do we have to plug in to get b?
Now,
Uh,
Yep, hello? Yeah, so what do we plug
yeah.
in for y and x?
We got another formula we can use to find the constant. Uh, whatever.
Hmm.
So the b is the constant there. So if the constant is not given, then we can use a formula that says y1, y2 minus y1 is equal to mx plus b.
Right.
That formula. You can use that
Well,
formula
it's
to
not
find.
y2 minus y1 is equal to mx plus b. I mean, y2 is equal to mx2 plus b, and y1 is
Yeah.
equal to mx1 plus b.
I mean, we can use that formula to. Right?
Sorry?
We can use that formula to find b.
Right. So what do we plug in? Right. I mean, but I think this formula is the easiest way to find b, right? We have y minus 13x equals b. So we just need to plug in the right numbers for x and for y. And we actually have two choices, both of which will work.
yeah, that's it.
Yeah.
That's a that replace y for 100
Hmm.
minus
Well, so let's be careful. What does this, the 100 an
sorry,
x value or
200,
a y value?
220,
Right. Okay.
2,200.
2200. Yes. Okay, good.
Yes,
So this will be 2200
yeah,
minus 13 times.
minus 13 times 100
Exactly.
is equal to b.
Great. And so this gives us that b is equal to 900. And you could have used the other point also. If you wanted to, you could have done x equals 300 and y equals 4,800. And that would have been fine also. And it will actually give you the same answer, 900 for b. Okay, so this gives us the b that we want, that it's 900. Exactly. So our final answer, let me just write it over here. Final answer is going to be the function f of x is equal to 13x plus 900. Okay, that's the linear function that we want. I'm sorry that the writing is a little bit small over here. Okay, so usually this is the best way to find a linear function that passes through 2 data points. And that's all the information you need for a linear function is 2 points. Because once you have 2 points, there's only one line that goes between them. So this tells you exactly what the function is. So this here is the graph of y equals 13x plus 900. So you first figure out the slope using the slope formula, rise over run. And then you figure out b by just plugging in one of the points to the equation here. And you can choose either point to plug in. And if you did the slope correctly, then plugging in either point will give you the same answer. Okay. Okay, so any questions about this one? Okay, good. It's clear. Okay, so that's our linear function. We'll keep that in mind. Okay, so homework exercise 2. Let f of x equal 3x plus 4 and g of x is 4x plus 7. Let's compute f of g of x and g of f of x. Okay, so remember what this means. It means that we plug one function into the other, right? So I have f of g of x here is equal to what? Well, we can write it as f of 4x plus 7. And what does that mean when we compose our functions, right? It means we plug in 4x plus 7 into f of x. So what expression do we get that if we want to expand that out? What does that give us?
12x plus 25.
Okay, but what's the intermediate step before we see the final answer? What do we have to write down?
Paragraph?
Yep. James?
X plus 7 is closest.
Sorry.
Plus 4.
Right. Okay, so 3 times 4x plus 7 plus 4. Right? This is the point, right? We plug in 4x plus 7 into 3x plus 4. And so this gives, if we expand this out, this is 12x plus 21 plus 4, which is equal to 12x plus 25, which is what Enoch said. Right? So there we are. Okay, so we get 12x plus 25 when we plug in the functions this way. Right? And in the opposite order, we have g of f of x, which remember we said last time, if you compose functions in 2 different orders, you don't expect to get the same result, right? The order matters when composing functions. So this gives us g of f of x, which is 3x plus 4. And so what happens when we expand this out?
It's going to be 12x plus 23.
Right, that's what it's going to come out. Because if we do the same thing, we plug in g, that's 4x plus 7, but we have a 3x plus 4, which we put in for the x. So this is going to be 4 times 3x plus 4 plus 7, right? This is what we're plugging in over here. Here we plug in, g of x. Here we're plugging in f of x. And then this is going to give us 12x plus 16 plus 7. And as Enoch said, that simplifies to 12x plus 23. Okay, so in this example, right, if we compose the functions in one order and in the other order, we get 2 functions that are pretty close. They're almost the same function, but they're not exactly the same. One of them is 12x plus 25, and the other one is 12x plus 23. Okay, so it just illustrates that you can get different answers even with very simple functions if you compose them in different orders. Okay, any questions on this? Okay, no questions. We'll move on. So exercise 3. So let's say that we have 2 linear functions, right? These are both linear functions. So if I have f of x equals mx plus b and g of x equals nx plus c, And here what's implied is that M, B, N, and C are all constants. Okay. So the question is F following G linear? Remember that as a function, that just means taking F of G of X. And if it is linear, can we calculate its slope? Right, so to do this, we just have to do the same thing, right? We want to figure it out. So F of G of X is equal to, well, what is it? It's F of G of X is NX plus C. NX plus C. And that is, what do we have? Well, we have MX plus B, but you have to plug in NX plus C here. So you get M times NX plus C plus B, right? You're always just plugging in the G of X over here. And if yes, keep going. Yep, Enoch.
Yeah. What if I say that the answer is linear?
Yeah, that's right.
Okay.
What happens when we do this all out? We get MNX plus MC plus B. And there's a lot of letters floating around. But Enoch, can you explain why is this linear?
Yeah. Hello?
Yes, hello.
Yeah, I would say it's linear because the power of x, is 1.
Mm-hmm. Exactly, right? So the point is all these other letters are just constants. Everything here is a constant. So as Enoch said, you have a constant times x to the 1, a single power of x, plus, and then this MC plus B is just another constant. It's just something that's made up of constants, so it's still a constant, okay? It's not a variable. So even though it looks like you're multiplying lots of things together, this is actually just a linear function because it's got 1 power of x and then a constant term, okay? So this is linear. And what's its slope in this case?
What?
And so what is the slope of this linear function? Okay, so Robert answered in the chat.
Yeah.
The slope is...
Yeah, the slope is mn.
Exactly. Thank you. Yeah, so Robert says, so mn is the slope. Okay. And so another way that you can say this, and this is actually going to be important when we end up talking about what's called the chain rule in calculus for derivatives, is that if you have two linear functions and you compose them, then the slope of the composition is the product of the two slopes. Okay, so
yes,
n here is the slope of f, and n here is the slope of g. And if you take the composition, f following g, then the slope is m times n. So the slope of the composition is the product of the slopes. And it turns out that if you did g times f, g following f, you wouldn't get exactly the same function, but you would get the same slope. The slope is still going to be mn. Okay? And we're going to see this, in another more complicated version when we talk about the chain rule, which can be summed up as saying that the derivative of a composition is the product of the derivatives. So we'll talk about that in much more detail later on. But this is really the reason, if you've seen any calculus before, this is the reason the chain rule works. Okay, is that if you compose two linear functions, the slopes multiply. Okay. Note that if you just multiply two linear functions, then you don't get a linear function at all, right? If I multiply mx plus b by nx plus c, I get something with an x squared term. And so that's not even a linear function at all. So I can't talk about what happens with the slopes when I multiply. Say I don't even get a linear function. But if I compose linear functions, I do get a linear function, and the slope that I get is the product of the other two slopes. Okay, any questions on this example?
Yeah.
Yes, James?
The operas find it difficult to understand how we get m times n to be the slope of the linear function there. I'm right now understanding that.
Okay, so let me use capital letters let me get a new color. Okay, so let's go do this in green. So one thing that you can think of is, what is this function? Well, it's something here times x. I'll use a capital M for that, plus some other constant. I'll use a capital B for that, right? So what we've written down here is we have this new function that's given by, our new function f of g of x is equal to mx plus b when I use this capital M and capital B, right? F of g of x is capital MX plus capital B, right? And what is my capital M here? It's MN, right? That's what's getting multiplied by the x. That's what gives it the slope. And what's my capital B? It's MC plus B. That's what gives the y-intercept. Okay, so this M over here is the slope. That's what the formula is.
Yeah,
and it's made up from these constants.
uh,
Is that okay?
can I also? Yeah, I want to add up to the explanation you just did doing.
Mm-hmm.
Yeah, probably in mathematics, if you have the slope written in the intercept form,
Mm-hmm.
where you have y is equal to ms plus b,
Mm-hmm.
you should always know that the coefficient of x is always the slope in our problem, and the b which is represented is the y-intercept. So for instance, if you have AB, if you have CD coming before or standing as the coefficient for x, is always the slope. So it won't actually be number always. Sometimes it will be in fraction. You will see 1 over 2. You will see 1 over 2s plus 4. You will see 1 over 2s plus 5. 13 over 7s plus 17. So it will be like a kind of amazing number. So anything that stands as the coefficient in the slope intercept form for x is always the slope itself. Putting it back, it will always give you a slope line. So
exactly right. Is that helpful, James? All clear?
Yeah, that's very, very good. Thank you.
Great. Okay, other questions? Okay. All right, so let's just go to the last one before we move on. So this is just examples. So can we think of two different examples of increasing functions, decreasing functions, odd functions, and even functions? And I mean, I guess we should remember the definitions of this. Remember, an odd function means that f of minus x is equal to minus f of x. An even function means that f of minus x is just equal to f of x. We did these last time. An increasing function means that if a is less than b, this implies that f of a is less than f of b. And a decreasing function means that if a is less than b, this implies that f of b is less than f of a. Okay, so a decreasing function goes down, an increasing function goes up, and an even function is the same whether you plug in positive or negative, and an odd function is the same. If you plug in a negative value, then it negates the function. So let's look, what do we have? So increasing, decreasing, even, odd, and even. And it's okay if some of the same examples work for more than one of these categories. Okay, so what's an example of an increasing function? So these are all going to be functions on the real numbers. That's our underlying assumption. We start with the real numbers and we finish with the real numbers.
Yeah.
Mm-hmm.
Yeah, it might probably be when you have in the case of A and B, if you have A to be equal to 2 and B is equal to 4.
Mm-hmm. Right. Well, but so remember, this has to work for a function to be increasing, this has to hold for every A and B, right? So
Yeah.
anytime you have a bigger input, you have to get a bigger output. And for decreasing, anytime you have a bigger input, you have to get a smaller output. So maybe I'll give an example for increasing. We've already seen one, right? This linear function here is an increasing function, right? Oh, x plus 4. Yes, I see. So from Robert Sunday. Yes, exactly right. So why don't we just do that, right? So f of x equals x plus 4 is definitely an increasing function, right? If I plug in something bigger to start, then I get something bigger out. So f of x equals x plus 4 definitely works. You see that as a line that slopes upward. That makes it increasing. And what about another one?
Yes.
Yes, James?
Yeah. F of x minus 4.
F of x equals x minus 4. Yeah, that works perfectly well also. Great. So these are two examples, right? Because in both cases, the plus and the minus 4 are not what matter, right? If I draw these graphs, in both cases, the x plus 4 looks like this. The x minus 4 looks like this, right? So this is y equals x plus 4, and this is y equals x minus 4, right? It's just the intercept which is different. One of them goes through the y-axis at 4, and the other one goes through the y-axis at minus 4, but they both slope upwards, right? So they're both increasing functions, right? If I plug in something further to the right, then the function goes up. It makes things bigger. Okay, great. Examples for decreasing functions? Right, so Robert's exactly right. For a linear function to be increasing, the slope has to be positive, right? Now, in general, we have increasing functions that are not necessarily linear, but if they're linear functions, exactly, you need the slope to be positive. All right, examples for decreasing functions? Well, we could do linear functions, right? So if a positive slope means increasing, so for decreasing, we could have a negative slope, right? So if I mean, we could just do the same two things, but with a negative slope, right? We could have f of x equals negative x plus 4, or f of x equals negative x minus 4. These will have negative slopes. If you want to look at it that way, one of them is going to look like this, and the other one is going to look like this, right? So this is y equals negative x plus 4, and this here is y equals negative x minus 4. Okay, and these are with negative slopes, so these are going to be decreasing. Right. Is that okay? Questions on this? Sorry. Keep everybody on mute unless you're answering a question or asking one. Okay, what about an odd function? Remember, we saw some pictures of odd functions last time, that when you plug in the negative, it actually negates. Okay, so Robert, yes, exactly, great. So f of x equals x cubed is an odd function. Great, right? Because if I plug in minus x here for x, I get negative x cubed, right? And we see why this is called an odd function, right? Because the exponent is odd. This is actually why they use the definition odd function, okay? Because when you raise x to the 3, it's an odd exponent, and that's going to give you an odd function, right? Because if I plug in minus x for x over here, I get something odd. Okay, what about my next one? F of x, what's another example? An x to the 5, exactly. So f of x equals x to the 5, this works. And in fact, any odd exponent will also work. X to the 7, x to the 9, and so on. And then with even functions, exactly the same thing, but, right, you can use even numbers instead. So f of x equals x squared, or f of x equals x to the 4. These are both even functions, right? If I plug in minus x for x, it doesn't change the function, right? Minus x squared is the same thing as x squared, right? Minus x squared is just the same thing as regular x squared. Minus x to the fourth is just the same thing as regular x to the fourth. And you should know some other examples of this. One of the ones that's also an even function, an odd function over here, is one of the trigonometric functions. So sine of x turns out to be an odd function. I think we mentioned this last time. F of x equals cosine of x is an even function. Another good even function is f of x equals the absolute value of x. This is going to correspond to, because, right, if you plug in a number or it's negative, you get the same results for absolute value of x. Okay? So, and there's lots more examples. Yeah, and x to the sixth, x to the eighth, exactly. Lots and lots of examples of what will give you an even function. Okay? So, you know, it's always good to just try to come up with some more examples on your own, but here we have some of the most basic examples of increasing and decreasing and odd and even functions. Okay? Any other questions?
Yeah, Dada Obus?
Yes, Theophilus, do you have a question?
Yeah, Princeton.
Oh, okay, Princeton. No, I saw Theophilus raising hand, but okay, Princeton, you can ask first.
Okay. So that means if we are using the odd number
Mm-hmm.
with the exponent,
Mm-hmm.
will it be with exponent?
Mm-hmm.
Okay.
Yeah. So if you use an odd number, if you have a polynomial where all of the terms have odd numbers in their exponents, then it's going to end up being an odd function. If the terms all have even numbers in their exponents, then it's going to be an even function.
Okay, thank you.
Okay. Great. Any questions? Any other questions?
Yeah, that Robert.
Yes, Abraham.
Yeah, I'm saying you are saying the f of x is equal to the sum of x is all function, but then cosine, when it is equal to cosine of x, it is even function. I want to know why.
Okay, yeah. So for now, I'll just show it to you based on the graph. To get to the real y of it, we'd need to go deeper into trigonometry. But let me look at f of x equals sine of x. I'm going to show you the graph. And then f of x equals cosine of x. I'll show you the graph. So f of x equals sine of x. The graph looks like this. It's a sine wave over here. And this here is -1. It goes between -1 and 1. This here is pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi. And similarly, we have minus pi over 2 and minus pi and minus 3 pi over 2 and minus 2 pi. Sorry if the writing's a little small. So what we see here is that if you plug in some x value, let's say over here, if this is x, this here is going to be f of x. And now what happens if you plug in the negative x value? So this over here is negative x. Well, over here, well, this, because it lies on the graph, this is f of negative x. But what you see from looking at the graph from this symmetry is that this value, this y value here, is exactly the negative of this y value here. So this f of minus x is exactly the negative of f of x. And this is what it means to have an odd function. Okay, and this pattern holds. Somehow, whenever if you go up to the right, it's going down when you go to the left. And it's always staying to be exactly the negative of what you get over here. So another way of seeing this visually is that this graph has rotational symmetry. If you rotate it 180 degrees around the origin, then the graph stays the same. Okay? But really, algebraically, another way to see it is that we have the identity sine of minus x is equal to negative sine of x. This is an identity. And to get into this, I'd have to go a little bit more into trigonometry, which I don't want to do right now. But the point is that this is a trig identity. So if you plug in minus x to sine, then you end up getting the negative answer. And so that tells us that this is an odd function. And for cosine, the graph looks almost the same, but it's a little bit different. It's a little shifted. Looks like this, -1 and 1. And here what you see is that it's symmetric over the y-axis. Right? And if this is symmetric over the y-axis, what happens is that if I plug in some x over here, and I have, this over here is f of x, the y value, then if I plug in negative x over here, the y value over here is still the same. And algebraically, the way we say that is that cosine of negative x is just cosine of x. They're the same thing, okay? Whereas sine of negative x is negative sine of x. That's the odd function property. Here, cosine of negative x is just cosine of x. That's the even function property, okay? And again, to get into why that's true, we really have to spend some time talking about trigonometry, which, can do, maybe actually I'll direct you to a video of one of the lectures from last time. Yep.
Hello.
Hello, yes?
Yeah, it's Enoch. It's Enoch.
Mm-hmm.
Yeah, like he was saying, so it actually implies that if only if anytime I input a value for sine x, I take any negative number, the value will be negative, right?
Right. That's what this identity means.
Yeah. So which mean if I want to take for instance, I'm taking SQ, I'm taking S to the fifth, I'm taking sine x, I'm taking cosecant, I'm taking tangent, I'm taking cos. Because okay, so yeah, okay, and for those evening, I will take S square, I take S to the fourth, I taking cosine x and secant x, because even it's only cosine and secant that work in this direction.
Yeah, exactly. So yeah, so these are all your basic even functions. So they're all the functions that satisfy an identity that looks like this.
Yeah.
Okay. Is that clear? Is everybody okay?
Yeah, thank you, Dr. Roberts.
Okay, you're welcome. Okay, let's move on to topic today. Oh, Theophilus, I saw you have a hand raised. Question? No. Okay. So, all right. So remember last time in class, 2 weeks ago, we discussed lots of different types of functions. We had linear functions and polynomial functions and rational functions and power functions, exponential functions, trigonometric functions, lots of different kinds of functions. And it turns out that the linear functions are actually going to be the most important ones in calculus. So we won't see that for another few weeks, but the linear functions are going to be the most important ones. And at least in differential calculus, kind of a lot of what we want to do is to take arbitrary functions or arbitrary what are called differentiable functions and turn them into linear functions. We want to approximate them by linear functions as well as possible because we understand linear functions very well, right? We understand that they're given by y equals mx plus b, that we can analyze them based on their slope and based on their intercepts. And so if we can, and other functions are more complicated. So if we can kind of make them linear, then this makes life a lot easier and makes it so that we can analyze these functions. Okay, so this is what we did last time. So today I want to talk about this new concept, which is going to underlie all of calculus, and that's called the concept of limits. Okay, so we're going to discuss the idea of a limit, and the limit is really the main concept that underlies all of calculus. So it underlies both differential calculus and integral calculus, although this semester will be focused on differential and probably most of next semester also. So suppose that we're given a function, say f of x, and let's say that function is defined near some x value, some point a. So you can just think of a as some constant. It's defined near x equals 2 or x equals 1 or something like that. What do I mean by near? This is a little bit vague, right? What I really mean is in an open interval containing a. So if I want it to be defined near 2, that means it should be defined on an open interval like 1 to 3. And of course, if it's defined on all the real numbers, then that's great, right? What we don't want is something, like f of x equals square root of x. You don't want to take a equals -5 because square root of x is not defined anywhere near -5 because it's not defined for any negative number at all to begin with. Okay? So if it's defined near x equals a, the idea of the limit is to determine what value does f of x approach as x approaches a. Okay, this is the idea of limit. And the way I state it now, it's a little bit vague, right? We're used to mathematics being very precise. To say, what does f of x approach as x approaches a sounds a little bit imprecise. This can be made precise. It is not that easy to make it precise, and I don't think we're going to do it this semester. And to make it precise, maybe some of you have seen, you have to use epsilons and deltas, and it's these complicated statements. They're in the textbook if you want to look at them, with the textbook that I sent the soft copy to the WhatsApp. But we're not going to go that route. Just to really understand it would take a lot of time, and I want to get a little bit more into the practical calculus applications. And if we really spent a lot of time on epsilons and deltas, I don't think we'd be able to get to them. So we're not going to be able to do that, but we will do a little bit better than this statement above. We'll make the definition a little bit better. We'll give an actual definition. But before we do any definitions and say, what a limit, actually define what a limit means, let's try to do some numerical experiments, okay? Sometimes it's hard to just start math by giving a definition and then going. It's better to kind of feel what the math is like first. And then once you have a feeling for it, then a definition will make some more sense. Okay? And so if you're following along, the material that we're doing today is based on sections 1.3 and 1.4 of the textbook. Okay? All right. So let's try to first get a feel of what limit should mean. So let's consider this function x squared plus x. And let's try to understand the limit of this function as x approaches 1. Okay? So what do we have? So what I'm going to do is just write a table of values. Okay? And what I'm going to do is I'm going to take some values that get close and close to 1. So in one column, I'm going to have x. And in the other column, I'm going to have f of x. Okay? And so what I'm going to do is I'm going to take numbers that are getting closer and closer to 1. So maybe I'll start with 2, and then I'll do 1.1, and then 1.01, and then maybe 1.001. Okay, these will be some nice values. And so let's see what happens when I plug all of these values into f of x. Well, if I take 2 and I plug it into f of x, I get 2 squared plus 2. That's going to be 6. If I take 1.1 and I plug it into f of x, you can just do that with a calculator, plus 1.1. This turns out to be 2.31. If I take 1.01 and I plug it into f of x, this turns out to be 2.1201. Sorry, 2.0301. Right, I'm just taking the number and I'm squaring it, and then I'm adding it to itself. And then if I take 1.001 and I plug it into x, then this gives me 2.003001. And maybe I'll just do one more. By then we'll see the pattern. If I get even closer to 1, I do 1.0001, then I'm going to end up getting 2.00030001. Okay. So what does it look like is happening if I'm getting, these numbers are getting closer and closer to 1? What's happening with my f of x? What are these numbers approaching?
Yeah.
Yep.
Yeah. As you get close and closer to 1, the value, the f of x, which is the function on the number line or on the axis, it gets closer to 2, but it doesn't really reach to 2. It gets
Exactly.
very, very close.
Right, exactly. So it looks like it's getting close to 2. It doesn't reach 2. But it looks like f of x is approaching 2. And that the closer and closer we get to 1, the closer and closer f of x is going to get to 2. And now, of course, this is a nice what's going to be called continuous polynomial function. If you plug in x actually equals 1, then f of x does equal to 2, right? So this is kind of an aside. F of 1 is, in fact, equal to 2, right? If I plug in 1, I get 1 squared plus 1. But this is kind of an accident. This is not relevant to calculating the limit. Okay, so this is a little bit counterintuitive, but when we're asking about limits, we're asking what happens when you get near to the value. We're not asking what happens exactly at the value itself. Okay? So for a lot of basic functions, those two things are the same question, right? So for a function like x squared plus x, saying what happens when you get near 1, what's the limit, is the same thing as just saying what do you get when you plug in 1. So for a nice, easy function like this, the limit question is the same question as saying plug in 1, what's the answer, right? But for other functions that we're going to see today, they're not the same question, okay? And the concept of limit is going to be most important when we're looking at these kind of more complicated functions where plugging in the number is not the same thing as getting close to the number, okay? So for this, we just start with this example. Okay, as we get closer and closer to 1, as x gets closer and closer to 1, it looks like f of x is getting closer and closer to 2. It looks like f of x is going to approach 2 over here. Okay? And this is in fact correct. It does get to 2. And the way we write this in terms of the notation, we write that the limit as x approaches 1 of f of x, or well, in this case, I'll say of x squared plus x, is equal to 2. Okay, so the notation is the limit as x goes to 1. We write limit x goes to 1. You just write lim. And then here you write the functions. So you could write x squared plus x, or you could write f of x. And we say that the limit is 2. That means that when you get close to 1, the function gets close to 2. All right, so we'll see some more examples to start to feel this. If you haven't seen limits before, it's a bit weird, right? It seems like we're not doing something very concrete. And the goal by the end of today is to feel like this is a little bit more concrete than it might seem at first. Okay, so we're going to move on to another example where we're really going to see the difference between a limit and just plugging something in. But before we move on to that example, are there any questions about this, what we have here?
Yeah, that all bones.
Yeah.
What if I was given a limit and the limiting value was given to be, for instance, s approaches 1 of the limit of L of any value L. So what can I say about the value of that function?
Right. So the value at 1, you can't say anything. We're going to see an example of this. Yeah.
Because the one I learned is that if the limit approaches any limited value of a constant, then the solution to that limit is the constant itself.
Okay, if it's a constant, yes. For certain polynomial functions, that works, but for general functions, it doesn't work. So we'll see some examples today. Okay. Other questions? Okay. So let's look at one that's maybe a little okay, so this is just recapping what I said. So from what we said on the previous page, it seems to make sense that the limit as x approaches 1 if x squared plus x is 2. Intuitively, what this means is that the function x squared plus x is continuous at x equals 1. And so the limit as x approaches 1 should just be the same as evaluating the function at 1. Let me graph this function. What does x squared plus x look like? It's going to actually have, so it's going to look kind of like this. Let me draw it correctly. It is a parabola, but it's centered at -1/2 instead of at 1, right? So it's going to look kind of like this. This is the graph of y equals x squared plus x. And the function, if we plug in 1 over here, and this is the point 2, we see that the point, 1 comma 2 lies on this graph. Okay. And as the x values get close to 1, the y values get close to 2. And in fact, when you plug in 1, you get 2. Okay, and so this just means, so what we say, and we'll talk about this in more detail next time, is that the function is continuous at x equals 1, meaning when you get close to 1, you actually get close to the value that you get when you plug in 1. So we'll talk about this in more detail a little bit later, but you can just intuitively see that this looks continuous. You draw it in one line. You don't have to make any skips or jumps or anything like that when you draw this function. Okay. Enoch, did you have a comment?
Yeah, I wanted to say something. This you have brought something to my mind that shows that limit, derivative, or integration, they are all connected, because if you get to do integration, they will introduce you to a topical area under the curve. So this one, it also carries my mind where you have the area from the curve, the area where the curve comes from the origin to the point 1, 2 and down to 1. That area under the curve is very integrated. They can also use the same or integration to find this area, the area you can be shaded.
Yeah. So you can do that, but we've got a ways to go before we can really talk about that here. Yeah. So okay, so that's this function. Okay. Second example, maybe a little less familiar. So let's consider the function f of x equals sine of x over x. And we're going to try to understand the limit of this function as x approaches 0. So
yeah,
we'll do the same thing. We're going to do a table of values. So table of values. Sorry.
Mr. Obos?
Yep.
Yeah, what if because there's a rules in limit where if you have this value of the function of x all over x, it should give you 1. This is a rules, because you will see if you put in a value of sin x or sin x to be 0, it will give you 0, and x, and you put in the value of x, it will also give 0, which will be 0 over 0. It will be in an indeterminate form. So yeah, so for this one, if you have the limit of true function of any true function of the angle or over that angle, it should be 1. Because
okay, but this is not. So this turns out to be right, but this is a very serious statement. This is not just something obvious, right? You need a serious geometric demonstration of this. So for now,
do it.
Okay, yes, but okay, we're not going to do it right now. So what I want to do is just because I'm trying to teach limit right now, so not necessarily do a big trig diagram. So there is a demonstration in the book if you want to see this, and maybe we'll do it next week. It's in chapter 1.4. But for now, I just want to try to teach this basic idea of limit, which is that what happens. This function is different from the other one. The other function we could just plug in 1 and guess the answer. But this function, if we want to take x approaching 0, so as Enoch said, we can't just plug in x equals 0. Because if we tried to do that, we would get that f of 0 is equal to sine of 0 over 0, right? And that's the same, sine of 0 is 0, right? So we would get 0 over 0, and this is right. This is what's called an indeterminate form. Indeterminate form. And what that means is 0 over 0 is it's undefined. It's not something that we can really, just from looking at 0 over 0, you can't tell what it should actually be. So this function, whatever it is, it's not defined at 0. It's got a gap. And so this is why the concept of limit is important, because the limit is still something you can do even if you can't actually plug in 0. So let's do our same thing. Let's look at values of x that get close to 0. So maybe we start with 1, and then we start with 0.1, and we have 0.01 and 0.001 and 0.0001 and so on. And let's see what happens when we plug this in to values of sine. So sine of 1, so I'm just going to do this on a calculator. You'll just take my word for it. So sine of 1 divided by 1 is about 0.84. Sine of 0.1 divided by 0.1 is 0.998. And if you do 0.01 divided by 0.01, this comes out to be 0.99998. And then if you plug in 0.001, this turns out to be 0.9999998. And then if you do another zero, these are all, by the way, approximates. These are not rational numbers. The decimals go on forever, but this is our pretty good approximation over 0.0001, then you get even more zeros. You get 0.999999998, and so on. Okay, so what does it look like is happening? As my input is getting closer and closer to zero, what is the output getting closer and closer to?
Yep.
Yep.
Yep, is actually getting close to one. Is getting close to one.
Right. See, we're throwing in lots of extra nines, and as we throw in more and more and more nines, this is getting close to one. So it looks like this is not a proof, but it looks like the limit as x approaches zero of sine x over x, it looks like this is equal to 1. Okay? So in fact, this is true. But you need to use some trigonometry to prove it.
Yeah, hello?
Yes,
yeah,
hello?
it's Enoch.
Yeah.
Yeah, in the same form of this function. What if the function I have is something like 3s over x, or like sin 3s over x, the limit at x approaches 0 of sin 3s over x.
Right. It turns out that's going to be 3. But that's also, I mean, you have to do a little bit of work to see that, right? So that's another example that you can do. It turns out if you have sine of 3x over x, you're going to get 3 as the limit as x approaches 0. But for now, maybe again, we'll talk a little bit more about calculating some of these types of limits later on. But for now, I just want to, show people that this is how the concept of limit works, right? Even if we can't, plug in x equals 0, we can still get close to 0, and these numbers get close to 1. So we can still say that the limit is 1. I mean, yes. So so Robert says, if sine x were replaced with the power series of sine x, the result would be 1, which could be a proof. So yes, there's a series some people may have seen that sine of x can be written as x minus x cubed over 3 plus over x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. If you haven't seen this, don't worry. But it's a little bit circular, right? Because in order to derive this series, you have to know what the derivative of sine of x is. And in order to know what the derivative of sine of x is, you need to know this limit. So you're kind of using this limit to prove itself, right? So at some point, you have to do a first proof. You have to actually do something. And the way that you can do that first proof is drawing a picture involving geometry and trigonometry. So we'll do maybe we'll do that proof next time. But for now, we see from numerical evidence that we at least believe that this limit is equal to 1, right? So in order to use this power series, you basically need to know this limit already in order to get that to work. Okay. Okay, but anybody more basic questions just about what's going on with limits here? Why is this working? Or why does this mean that the limit as x approaches 0 of sine x over x is 1? Or is everybody okay there? Okay, great. Okay, so second example continued. So this is again what we said. From what we've computed on the previous page, it makes sense to say that the limit as x approaches 1 of sine x over x is equal to 1.
Okay.
Yes.
Yes,
Enoch.
Yeah. This is the same thing I was saying. This is the same thing I was saying in the case for the first time where you have the limit at s approaching a of f of x equal L. It was the same thing I was referring to earlier.
Oh, okay, so this definition right here. Yeah. So let's see what the definition is. So this is going to be what I'll call a half rigorous definition. It's not a fully rigorous definition. For that you need epsilons and deltas, but this will at least be a little bit more precise than what we've said about approaching. So what this says is, suppose that f of x is defined near x equals a. I already told you what that means. It has to be defined not just at a, but in some interval around a. So we say that, and maybe it's not defined at a. That's fine, right? Oh, sorry. Oh, this is a typo. This should say the limit as x approaches 0 of sine of x over x. And maybe I'm going to remark again, observe that sine of x over x is defined near x equals 0, but not at x equals 0. Right? As long as if I plug in anything else, anything that's not 0, if I plug in anything else, then I can plug that into sine of x over x. The only value I can't plug in is x equals 0. Everything else I can plug in. Okay? So our process can be summarized by this following definition. So let's say that f of x is defined near x equals a, but maybe not at a. It might be defined at a, it might not be. So we say that the limit as x approaches a of f of x equals L, this L here is for limit, means can we make the values of f of x arbitrarily close to L, meaning as close as we like, by taking x sufficiently close to a on either side, but not equal to a. So the definition is a little bit of a mouthful, and one observation from this definition is that the value of f of x at a does not affect the limit. Okay, so the value of f of x at a does not affect the limit. We only care, what happens as we get near to a. Okay, so let me say this one more time, kind of in the what do I want to say? Yeah, so kind of in the context of what we've been doing. So if we want to make, so why would the limit of sine of x over x be equal to 1? Well, the idea is, how close do we want to get to 1? Let's say I want to get within like 0.01 of 1. I want to get that close. Can I take x close enough to 0 to do that? And the answer is yeah, right? Look at this table of values. Once x gets this close to 0, I'm within 0.1 of 0, then it looks like sine of x over x is getting within 0.01 of 1, right? And if I want to get closer to 1, let's say I want to get within, 4 decimal places of 1, then that's fine. I just have to take x a little bit closer to 0. I take it to be 0.01. If I want to get within, 7 decimal places of 1, that's fine. I just have to take x even closer to 0. So you should think of a limit as saying, what does it mean to say that the limit is 1? Well, if you give me some number close to 1, I can tell you how close to 0 you need to get in order to do that. Okay, I mean, this basically is the epsilon delta formulation of limit, just sounding a little bit less technical. Okay, so you can get as close to 1 with the value as you want by taking x close enough to 0. Or likewise, with our first example, you can get the result as close to 2 as you want by taking values of x that are close to 1. Okay? You're not allowed to take x equals 1. You have to take values of x that are close to 1. But it's saying that if you get close enough to 1, then f of x is going to be close enough to 2, as close as you want to make it. Okay, so this is what a limit means. All right, so it means you can make f of x get as close as you want to L by taking x close enough to a. Okay, this is what it means to say that the limit as x approaches a of f of x equals L. And this is a definition that takes a little bit of time to come to terms with. So we're gonna keep doing some more examples that will hopefully make this clear. But hopefully, at least seeing these tables of values, you kind of see what's going on, right? You can get as close as you want there it closes what you want on the output by taking a close enough input. Okay. Any questions? So let's do some more examples. So a third example. Let's consider the function f of x equals x squared minus 4 divided by x minus 2. This is defined for every real number x except 2, right? Because I can't plug in 2 here because I get 0 over 0, right? So let's try to understand the limit of this function as x approaches 2. Now, some people may see the answer already, but let's still, just because we're still working with the concept of limit, let's still look at a table of values. And maybe this time we'll do it a little different. We're going to talk next time about one-sided limits, but we've always been approaching things from the right side. Let's try to approach things from the left side. So let's approach 2 by first plugging in 1.9 and then 1.99 and then 1.999 and so on. So let's see what happens, as x approaches 2. So, right, and remember, we can't actually plug in x equals 2 because you're going to get 0 over 0 if you try to plug in x equals 2. Okay. So what do we get here? Yes, Princeton.
Yes, Dr. Ogle.
Yep.
Yeah, we've been starting with this value and I've been confused finding the placing x value that is not given the problem. I don't know whether we are looking for a number that will be approaching 2, but I think 1.9.
Right. Yeah, so I'm just starting with a number that's kind of close to 2 and then getting closer.
Okay.
Right. There isn't one number that is as close to 2 as possible. If I have a number that's close to 2, I can always get closer, right? So I'm just starting, just as an example, start with something pretty close, get a little closer, get a little closer. Hopefully this will tell us what's going on.
Okay. If example, we are using the 3. If we are using the 3. No?
Right. Yeah, you could start with 3 and then you
the number. So the number that will be approaching the 3 will be, can we use 2.9 as the starting point, right?
Yeah, exactly. Definitely. Great. So, Alexander, you have a question?
Not question per se. I was just trying to add up to make my own point to what you're saying. The number should not always, no matter what you do, the number should not be equal to x. It should always be maybe something less than that.
Right. Do not use x equals 2. Right. And in this case, we can't use x equals 2 because if you plug in x equals 2 here, you won't get an answer. You're going to get 0 over 0. It doesn't work, right? So let's see what we've got. So it turns out that when you plug in 1.9 here, you're going to get 3.9. And when you plug in 1.99 here, you're going to get 3.99. And when you plug in 1.999 here, you're going to get 3.999. Again, you can do this with a calculator, plug it in, and see what you get. Okay?
Yes, Yeah, that over?
Yeah.
Yes, I also want to add on to him for clarity, Actually, the limiting value, if they say limiting value, which is the number that the value always approaches from the function. If you have, for instance, if you have x approaches 2 or x approaches 3, approaches 5, if the approaches, it doesn't mean the value given is 5. It means these are number very close to this number that you are evaluating the function at. For instance, if an instructor gives you evaluate this limit as x approaches 2, you are not exactly. It doesn't exactly mean that this is 2. It means these are values that if you increases or decreases, they either carry you to 2 or it take you away 2. This value might be, for instance, those values that are very close to 2 can be 3.99, you can take 2.1, you can take 2.11, you can take 2.111, you can take 1.9.
2.001. Yeah.
Okay, just like that.
Yeah. Yeah, exactly. Right. So we're getting close. And so in this case, what does it look like? It looks like, and then Harrison, I'll answer your question. So it looks like here that the limit as x approaches 2 of this f of x looks like these numbers are getting close to, well, we got 3.9, 3.99, 3.999. Yes. James?
Yeah. So you mean you will square 1.9 and minus 4 divided by 3.9 minus 2. I will give her 3.9.
Yeah. Yes.
Okay.
Yeah, maybe I should do one explicitly, right? So what's going on here? This is just saying that 1.9 squared minus 4 divided by 1.9 minus
Yes,
2 turns
yes,
out that this is
that's,
exactly equal to 3.9.
okay. Now you see now the pattern is being to change as you move from 1.9 to 1.99. The value changes from 3.9 to 3.99, which means this limit is arbitrary or is actually approaching 4.
Exactly. Great. So this limit
Yes.
should be 4. Okay. And again, we haven't proved this. So Harrison asked a good question. Can you factor to solve this problem? And the answer is yes. And we're going to do it in 20 minutes. Okay. So for now, so right now we're still just looking at limits and seeing by looking at tables of values what they look like. What we're going to show at the end of today is how do we actually use factoring to solve this problem. Okay. So we're going to do that. Yeah. So the answer is 4. Exactly. Somebody else had a comment? And so the answer is 4. The answer will be
I
4.
want to understand something.
Yeah.
Yeah, so if I'm replacing X for, let's say, 2.01, will I still be correct to solve this problem?
Yeah, I just decided for a change. In our first examples, we got numbers that got very close to the limiting value from the top. You can also do it from the bottom. So this was just to show a different way, but you could definitely do 2.1 and 2.01 and 2.001. That's completely fine.
Yeah. So
and in fact, there's sometimes you'll get different results, not for anything today. So there's something called a left limit and a right limit, and we're going to talk about that next week.
yeah. So and actually the next way around to prove that this actually gets to 4 is that if you want to swap out x squared minus 4 as, because 4 can be written somehow at 2 squared, and you will have the difference or 2 squared, which is written in the form of a squared minus b squared, which is a plus b, a minus b, and you will know that the value will cancel out and you will be x plus 2. Now you can insert the value of x, which is 2, and you know that the problem in this whole thing that are causing our answer to go to 0 is the s minus 2. So you get the s minus 2 going to get out, and you only be left with s plus 2, which will be 4 exactly.
Yeah, so we're going to do that. We're going to do that exact same thing. Let's just wait 15 minutes because I want to prepare a little bit more to do that. I want to talk when we do that a little bit more carefully about why everything is justified, why everything's allowed to do that. Okay, so that's exactly right. And stay tuned. In 15 minutes, we're going to do that. Okay. So before we do that, any further questions on this example? Okay. Fourth example. Let's look at the function f of x equals 1 over x squared, defined for any real number x except 0, right? So this is still defined near 0, but it's not defined at 0. So what happens to this function as x approaches 0? So let's look at just 2 quick approaches. So there's a table of values approach. We can do the same thing. And then maybe we can also do a graphical approach. We can graph the function and see what it looks like. So if here I have x, and here I have 1 over x squared, we want to know what happens as x approaches 0. Okay, so let's take values that get closer and closer to 0. So maybe we'll start with 1, and then 0.1, and 0.01, and 0.001, and so on. Well, 1 over 1 squared is going to be 1. 1 over 0.1 squared turns out to be 100, right? This is equal to 1 over 0.1 squared. 1 over 0.01 squared turns out to be 10,000, and 1 over 0.0001 squared turns out to be 1 million. And if you graph this function, what it looks like is this. Okay, and you have what's called a vertical asymptote right here along the y-axis. Okay. So we see here is a little bit different, right? We take these values that are going close to 0, and we don't get that the outputs are converging to anything, right? In fact, they're getting bigger and bigger and bigger. It's not like our previous tables of values where these numbers were all getting close to 4, or in the earlier example where these numbers were all getting close to 1, or in the earlier example where these numbers were all getting close to 2, right? Here, they're not getting close. They're just growing and growing and growing without bound. And we see that if our x's start getting even closer to 0, then these 1 over x squared numbers will keep getting even bigger and bigger and bigger. Okay? So we have two ways of talking about this. So we say, in this case, since the values of 1 over x squared are not approaching any real number, that the limit as x approaches 1 of 1 over x squared, we say that this limit does not exist. Okay, so we say here that this limit does not exist because these values are not approaching any actual number. Oh, I see an answer for this. Yeah. So this exactly works, but I want to justify your steps. We'll do that in a little bit. So we say that this limit does not exist. Okay, so the limit does not exist. Or what you can say also, which maybe we'll again talk a little bit more about next time, you could say that the limit is infinity. Okay, that's a little bit trickier. It's not wrong. It's perfectly fine. So it looks like these numbers are growing without bound off to infinity. So if you want to, you could say that this limit is equals infinity. So say or equals infinity. But I just want to caution you, there are limits that do not exist and equal infinity, like this one, and there are other limits that do not exist and they're also not equal to infinity. Okay, so saying that the limit doesn't exist is not the same thing as saying that the limit equals infinity. And saying that it doesn't exist is the more, it's the broader category. It encompasses more problems. Okay, so it's safer, and at least for today, what we're going to say is that the limit does not exist. Okay, we'll talk a little bit more next time about what it means to say that the limit is infinity or that it's minus infinity or that it's neither of them. But for us, all that we see is that these values are not approaching any real number. Infinity is not a real number, so they're not approaching a real number. And so there's no real number that satisfies the definition of limit, and that means this limit does not exist. Okay. Alexander, I saw your hand raised for a little bit. Do you have a comment?
Yeah, so
Yes.
you already said, but next we will talk more about it. So there's no need. Because we
Okay.
want to know what are the instances to say that the limit does not exist or the limit is infinity or not.
Okay, so that will be the focus of next class. All right, any other questions about this? Another reminder, by the way, just if you haven't written in the comments yet, if you haven't written your name yet, to please write it in. Just we want to make sure we have your record for data. Okay, so that's a fourth example. Okay, so what are our basic rules for evaluating limits? And I'm not going to prove all of these, or really any of them, but we're going to have this as our toolbox. So what's the first basic rule? If f of x is just some nice function, like a polynomial, or if it's a rational function where when you plug in x equals a, you don't get 0, so you don't have one of these bad cases where the denominator is 0, then it is true that the limit as x approaches a of f of x is just going to be f of a, right? This is like example 1. Right, example 1, what did we have? The limit as x approaches 1 of x squared plus x was just equal to 2, And this was just the same thing as plugging in 1 to the function. This was just 1 squared plus 1, right? And that worked because this here is a polynomial. Okay? And so this works for any polynomial or any rational function as long as the denominator is not 0 when you plug x in, or when you plug a in. Okay, so for these things, if you want to evaluate the limit, you can just plug in the value and it works. Okay, so maybe another example that I would say is like, if I want to take the limit as x approaches 0 of, 3x plus 4 over 2x minus 7, it turns out it will be good enough to just plug in x equals 0. This is just going to be 3 times 0 plus 4 over 2 times 0 minus 7. It's fine to plug it in because this denominator here is, this whole thing here is not equal to 0. So as long as it's a rational function and the denominator is not 0, you can just plug in, and this is going to give you negative 4/7.
Negative 4, so.
Yeah, so this is just going to be another example. Great. So this is maybe the most important rule for evaluating limits. If it's a polynomial or rational function, you just plug in, okay? In fact, if it's any continuous function, you just plug in, but that's not so helpful because I haven't told you what continuous means, and I'm not going to until next time. All right. So furthermore, I should say that limits respect all of the basic operations, all of the basic things you can do with functions. So plus and minus and times and divided by. And also if you do powers and if you do roots, then limits respect all of these operations. Let me say what that means. What that means is, let's say I've got two functions, f of x and g of x. And let's say that the limit as x approaches 4 of f of x is equal to 1, and the limit of x approaches 4 of g of x is equal to 2. Well, then if I add the two functions and I want to know what's the limit as x approaches 4 of the sum of those two functions, then I just get that I just add the limits. It's going to be 1 and 2, so I add them up and I'm going to get 3. Maybe in simpler terms, we'll do another example. What that means is if I have a limit that I want to evaluate and my function is broken up into pieces that are getting added together or that are getting multiplied together, then I can evaluate the limit by doing the pieces separately and then adding the results. So let me do actually one more example of this. So let's say that I wanted to do the example. So let's suppose we know that the limit as x approaches 0 of sine x over x is equal to 1, okay? We believe this right now, but I haven't really proven it to you. But for now, let's just accept that this is true. The limit as x approaches 0 of sine x over x is equal to 1. So then what is the limit? So what is the limit as x approaches 0 of sine x over x minus, and now let's look at this other, 3x plus 4 over 2x plus minus 7. Well, the point is, what we can do here is we can evaluate the two limits separately. So when I say that it respects plus and minus and times and divided by, what I mean is that this is equal to the limit as x approaches 0 of sine of x over x.
Yeah. What if I want to say the answer is 3 over 7?
Yeah, that'll work. So let me just do this out, right? So it's limit as x approaches 0 of sine of x over x minus the limit of as x approaches 0 of 3x plus 4 over 2x minus 7, right? The point is we can take these separate pieces and do the limits separately, and then we can subtract them. And now we know already that this is 1. That's this limit as x approaches 0 sine x over x. And then on the previous page, we saw that this limit was negative 4 over 7. Okay, so actually the answer is slightly off. So what we get is 1 minus negative 4 over 7. The minuses become pluses, and what we actually end up with is 11/7. Because we get 1 plus 4 over 7. Okay, so this is just to say that if you want to do limits, you can do them piece by piece. Okay, if you have something that you know plus or minus something else that you know, you do the two pieces separately and then add or subtract. If you have something you know multiplied by something else that you know, take the two pieces that you know, multiply them. And this even works for square roots and cube roots and powers, right? So another thing would be another example. Yes.
Yeah, is
Yeah.
Yeah, so which means this, if you have the function f of x to be something like 3x squared plus 2x plus 5, then they ask you to evaluate the limit of that function at x approaches 2. So you can distribute 3x squared, 2x different, and that of 5 different, right?
Right. Or you could use just the fact that that's a polynomial. So you know that you can just plug in that will work, or it's a polynomial. So you know you could just plug in x equals 2 and that will work too. Actually, the reason it works for polynomials is exactly because of what you said, because you can do each one separately. So yeah, what if the limit has the upper polynomial and the lower is monomial? So this example that you have there actually is going to have the limit is not going to exist. So this is going to be one of these infinite limits that we're going to talk about next time. Okay. For Princeton. But let me just say one other thing. If we had, you know, like the square root, let's say that we had the limit as x approaches 0 of the square root of sine x over x plus 1, something like this. Well, what you would get here is the point is you can pass the limit under the square root. You can just, this is just the same thing as the square root of the limit as x approaches 0 of sine x over x plus 1. And maybe, you know, let me just do this on another page just so that we have more space. So the limit as x approaches 0 of something like square root of sine x over x plus 1 should be equal to the square root of the limit as x approaches 0 of sine x over x plus 1. And that's equal to the square root. Now we can use the addition rule. It's just limit as x approaches 0 of sine x over x plus limit as x approaches 0 of 1. And we know what this is. The limit as x approaches 0 of sine x over x is just 1. And the limit as x approaches 0 of 1 is also just 1, right? This 1 is just a constant. It doesn't depend on x at all. So the limit is exactly going to be 1. So we just get square root of 1 plus 1, which ends up being square root of 2. Okay? So all that it means is that if you have standard mathematical functions like plus and minus and times and divided by and powers and square roots and cube roots and all of these things, in order to do the limit, you can just evaluate whatever limits you need inside the functions and then just apply the same functions in order to get the limit. So you want to do limit of this square root of this complicated expression, just take the limit of what's inside and do the square root. You want to do the limit of a sum, just take the limits individually and add them. Okay? So for standard functions, you can always just apply the limit to each piece and then evaluate the function. Okay, so questions about this example? Okay, so let's do 2 more examples today before we close. So now let's go back to what we have. So, and this is this thing that Harrison referred to and Enoch wrote up, right? So how do we actually evaluate this example 3? We did it with a table of values, and we saw that we think the answer is 4. But what do we actually do here? And I want to say this so carefully. So let's observe, so these are in Enoch's notes to the chat, that x squared minus 4 over x minus 2 is that x squared minus 4, you can factor it as x plus 2 divided by x minus 2 over x minus 2, right? And that this we can cancel out, but we have to be careful. If I want to cancel out the x minus 2 over the x minus 2, that this is equal to x plus 2, but I need to make a big warning. This is as long as x is not equal to 2. Right? I can't cancel x minus 2 over x minus 2 if x is equal to 2. Right? I can't do that because then this is nonsense. If x is equal to 2, this function doesn't even exist, whereas this function gives me 4. Right? So this equality here, x squared minus 4 over x minus 2 equals x plus 2, that's only okay if x is not equal to 2. Right? It's not okay if x is equal to 2. So you need x not equal to 2 in order to be able to say that. But the good news is that for the limit as x approaches 2, which is what we're trying to do, we don't care about what happens when x is equal to 2. Okay, so we don't care in this case about what happens when x is equal to 2. So making the cancellation is okay. So if we want to do this, I can say that the limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to the limit as x approaches 2 of x plus 2 times x minus 2 divided by x minus 2. This is completely fine. I'm just rewriting the numerator. And this is equal to the limit as x approaches 2 of x plus 2. Right? Because this limit only depends on values near 2. It does not depend on the value at 2. So making this cancellation is okay, because the cancellation would cause problems at 2, but the limit doesn't even see what the value at 2 is. It only sees the values at points near 2. Okay? So this cancellation is perfectly fine for any x that's close to 2. It's just not fine for x at 2. And we don't have to worry about that. So then, and now this is just a polynomial, so we can just use our rule of limits that this is just equal to what you get when you plug in 2. So it's just 2 plus 2, which is going to give you a 4. And this is because this is the polynomial limit rule. So Robert, I see you have a hand raised.
Yeah, it's something that I wanted to clarify.
Mm-hmm.
If you look at the original function, that is a rational function, right?
Yes. Mm-hmm.
And when you look at the function we have, which is x plus 2, after factoring, it's a polynomial function.
Right.
So what I wanted to say is that the original function 2 is not a it's not part of the domain.
So sorry, you're not coming in so clear.
Polynomial function that we have at the end, 2 is part of the domain. So we have 2 separate functions, but we are using the polynomial function, and we want to use the polynomial function to understand what happens to the rational function as x approaches 2. Right. It's just similar using system. That is what I wanted to say.
Yeah. So let me explain. So I think it didn't come in so clear, but I think I understand what you mean. So what is the difference between the rational function x squared minus 4 over x minus 2 and the polynomial function x plus 2? So maybe I'll write this on a new page. So what is the difference between x squared minus 4 over x minus 2 and x plus 2? Well, what do I get with the graphs of these functions? So y equals x plus 2 is easy. The graph just looks like a line. This is y equals x plus 2. And in particular, I have this point 2, 4 over here. And this is the point 2 comma 4. Now, this rational function, in fact, is exactly the same function as x plus 2. The only difference is it's not defined at 2. So if I'm drawing this, I'm going to draw the same function, but I have to put a little hole here. So if this is 2 and this is 4, this is the point 2 comma 4, and it is not on the graph. Okay, so these two functions have exactly the same graph, except when you consider it as a rational function, the graph has a hole in it right at 2. The graph has a hole in it right at 2, whereas when it's considered as a polynomial, the graph is just true everywhere. But in any case, the two functions are the same when x is not equal to 2. Those two functions are exactly the same when x is not equal to 2. It's just that this one does not have 2 in its domain, whereas this one does have 2 in the domain. So they're the same when x equals 2, which means that if I take the limit as x equals 2 of the two functions are the same. Right? Because if I have two functions that are completely the same, except that they're different at x equals 2, then their limits as x approach 2 have to be the same, because when I'm doing the limit as x approaches 2, the only values I'm looking at are values of x that are not 2, right? So the only ones I'm looking at are values of x that are not 2. And if I'm only looking at values of x that are not 2, then these two things are exactly the same function. So they've got to have the same limit, right? They only differ at x equals 2, where this one gives you 4 and this one is undefined. But regardless, for the limit, that doesn't matter, right? The limit is only using points that are not 2. And so that means the limit of this function has to be the same as the limit of this function. But this function is a polynomial, which means that you can calculate the limit just by plugging in. So that's what you do. Okay, so I hope this clarifies and maybe answers your question, Robert, is that the functions are exactly the same except at the point 2. But differences at the point 2 don't matter for evaluating the limit. Okay? Is that okay? Okay. So let's do the last example for today. So the last example is evaluate the following limit. Square root of, limit as x goes to 0 of square root of x plus 4 minus 2 over x. Okay? And one thing to notice, if you just try to plug in, x equals 0, what do you get? You get the square root of 0 plus 4 minus 2 over 0, which is 0 over 0. And again, that's one of these indeterminate forms. Okay, so this doesn't help you to try to plug in x equals 0 over here. So we're going to have kind of two approaches. Over here, let's just start with table of values.
Yeah, hello.
Yes.
That one.
Mm-hmm.
Yeah. What if I say that this one, the answer is probably 1 over 4. 1 over 4.
1 over 4. I think that's probably right. Yeah. So how do you get that?
Yeah, I solve it. I just solve it.
Okay. So yeah. So I'll let you solve it when we go for the solving,
Yeah,
but let's first just look at the table of values and then we'll solve this. Okay. So let me just first look at the table of values. Let's say that I try to plug in, 0.1 and 0.01 and 0.001. Let me just briefly, so this is x, and this is square root of x plus 4 minus 2 over x. So what do we see with this table of values? Let me see, square root of 4.1 minus 2 divided by 0.1. Okay, so this turns out to be 0.248. And then if I do this instead, this comes out to be 0.2498. And then if I do this instead, this turns out to be 0.24998. and so on. So seems like, as Enoch said, that the values are approaching 0.25 or 1/4, right? That's what it seems. Is this getting smaller and smaller? This looks like it's coming toward 1/4, right? So let's say we actually want to compute this rather than just using a table of values. So this is the table of values method. Now this is going to be our algebraic method. Okay, yes. So what do we do?
Yeah, for me, actually rationalize the numerator, because it is the most difficult part in the problem. So you have to multiply both the denominator and the numerator by the inverse of square root x plus 4 minus 2, both up and down. So you are going to get rid of it pretty soon.
So I think you mean the conjugate, right? So right? So we do this. We multiply. So this is a trick that we use with these radicals, is we multiply by the conjugate. So if you have something involving square roots that you can't simplify, one thing that you can try to do is multiply by the conjugate of the square root. The conjugate means if you're adding a square root to something, you subtract it instead. Or if you're subtracting a square root to something, then you add it instead. So what we're going to do here is multiply by square root of x plus 4 plus 2 divided by square root of x plus 4 plus 2, right? This is fine, right? This entire thing is just 1, right? I'm certainly allowed to multiply by 1. There's no problems there, right? And so what do we get? So we get that this is the limit as x approaches 0 of, well, the denominator, I'm just going to write it as x times square root of x plus 4 plus 2 for now. And in the numerator, the reason we do this is we get simplification, right? Because this is of the form a minus b times a plus b, where a is square root of x minus x plus 4 and b is 2. So if I do something like a minus b times something a plus b, I end up getting I end up getting a squared plus, is a squared minus b squared. So the square of x, so I get, square root of x plus 4 squared minus 2 squared. And so that's the limit as x approaches 0 of x plus 4 minus 4 divided by x times square root of x plus 4 plus 2. Or in other words, the limit as x approaches 0 of x divided by x times square root of x plus 4 plus 2. Is everybody okay so far? Any questions? Okay, so now what's the problem? If I just if I just plug in x equals 0, then I get 0 over 0. I still have a problem. But because it's a limit, I'm allowed to cancel the x and the x. I can cancel them again because x is not equal to 0, because we're taking a limit as x goes to 0. So we're only looking at values of x that are not 0. So in this case, I'm allowed to cancel the x and the x. I'll say because I can do this because x is not equal to 0. So I'm not dividing by 0. So this is okay. And so what we get is that this is the limit as x equals 0 of 1 divided by square root of x plus 4 plus 2. So let me complete the problem on the next page. So I'll just rewrite this. So this is the key step, is canceling the x's. Once you've multiplied by these conjugates, you can cancel the x's. And you can do that because you're taking a limit as x goes to 0, which means these x's are not going to be at 0. Okay, so let me finish this problem on the next page. So we're going to get the limit as x approaches 0 of 1 divided by square root of x plus 4 plus 2. And now we just use the limit rules, right? So we can say that this is the limit. We can do the limit of the numerator and the denominator, right? We can pass just everything through. This is the limit as x approaches 0 of 1 divided by the limit as x approaches 0 of square root of x plus 4 plus the limit as x approaches 0 of 2, right? I can just take the limit of every piece. That's what these rules say. And what is this? Well, the limit as x approaches 0 of 1 is just 1. Constants just stay the same. The limit as x approaches 0 of 2 is just 2. And the limit as x approaches 0 of x plus 4 is, remember, this is the same thing as the square root of the limit as x approaches 0 of x plus 4 plus 2. And over here again, all that you have to do is plug in because this is a polynomial. So this is going to be 1 over, you just plug in 0 to x plus 4. So you just get 4, square root of 4 plus 2. And this simplifies to 1 over 2 plus 2, which is 1 over 4. Okay. So there's 2 main steps here in this problem, or 3 main steps, let's say. The first one, well, first, the 0th step is realize that you can't just plug in x because you're going to get 0 over 0. So the first step is this trick. You multiply the numerator and the denominator by the same thing, which is the conjugate of this radical expression. So you're rationalizing the numerator. When you do that and you simplify, you end up getting x over this expression here. The second step is to cancel out the x's, which you can do because x is not 0, so you're not dividing by 0. And then the third step is to actually evaluate this limit. But this limit doesn't give you any problems. It's just using standard mathematical expressions, and nothing goes to 0. You're never dividing by 0 or anything like that. So in the end, when you evaluate a limit like this, you can just plug in x equals 0, and the answer that you're going to get is 1/4. These are your rules of limits. And from the beginning, if you wanted to, you can also see like this is actually right? I mean, if you're plugging in numbers that get closer and closer to 0, this really does get closer and closer to 1/4, right? So it makes sense that this here is the limit that you're looking for. Okay, so this is the trickiest example for today. It's the last example for today. Any questions on this? Okay. Okay, great. So, okay, so there's some homework questions. So there's 4 homework exercises for this time. So the first one is to use a table of values to guess the limit as h approaches 0. If you don't like h, you can call it x, of 2 plus h to the 5th minus 32 divided by h. Okay? Second problem, similar. Use a table of values to guess the limit as x approaches 1 of x to the 6th minus 1 over x to the 10 minus 1. Okay? Again, you try to just plug in x equals 1, you're going to get 0 over 0. So you're going to have a problem. Third one is to actually evaluate this limit as x approaches 2 of the rational function x squared minus 2x divided by x squared minus x minus 2. This will be similar to what we have. And then the fourth one is evaluate the limit as x goes to minus 1 of x to the 4th, that should say plus 3x, plus 6. And if you want more practice, you can look at the exercises in section 1.3 and 1.4 of the textbook.
That was?
Yes. Yes,
these exercise questions, like the 4 questions given here, when are we due to submit them?
For the next class. Just send them to the chat before the next class.
Okay. Can I
or send it to me on WhatsApp?
Okay, in your personal inbox, right?
Yeah, either my personal one on WhatsApp or you can just email it to me if you want.
Okay.
Oh, sorry, typo. Sorry. All right. Second one, yeah. So that's my personal email. You can always submit a solution to me if you want. Okay. And another logistical thing, there is no class next week, October 18th. I'm going to be away. So the next class is in 2 weeks. So October 25th, and we're going to discuss limits at infinity for the next class. Okay, so limits going to infinity and limits as the value goes to infinity also. Okay, so as always, I will send you I'll post the notes to the WhatsApp chat, and I'll post the recording to YouTube, and I'll let you know the link. Well, you have my YouTube link, all of the videos are on that link, but I'll send you the link as usual. And I hope this was enlightening. I think limits can be a hard topic, especially if you're not familiar with it, because they're for a lot of people, it doesn't feel as precise as the rest of math. But I guarantee you it is precise. That there is still only one right answer for any of these limit questions. And so if you're not familiar, it just takes a little bit of time working with them to get things to work. Okay? Yeah, okay, I'll repost the soft copy of the book. It's in the WhatsApp chat if you want to look, but I'll repost it. Okay? Any last questions? Okay, you're most welcome, everybody. Have a great weekend, and I will see you on October 25th in 2 weeks. All right.
So,
have a good.
Yes.
Yes, Abraham.
Hello.
Yeah, Abraham.
Yeah. So we have class on the 25th.
Class on the 25th. No class on the 18th.
Okay. Thank you for today.
All right, you're welcome.
We hope to see you on the 25th.
It sounds good. All right, have a good week, everyone.
Do not forget about Sange.
No, is she here? Oh, she's here. Yeah. Sange, did you need to say anything?
Hello.
Hello, yes.
Thank you for the class. And thanks everyone. Let's try to be serious with the time, because if we most of the time when you don't receive data and you come on the platform, I will do a reform. So I beg you, please make sure that you be in class, and let's be serious with the class, and listen too much of the class will not be so good for us. So I'm just advising every one of us to be on time and in class every time. Another thing is, some people you enter, you not write your name, you did your gadget name on it, so I won't be able to determine who is that person. So as soon you get simply log in and change your name. Thank you so much, Andrew. Andrew, you said one, and when will be no class on the 25th?
No, there's no class on the 18th. There is class on the 25th.
Okay, no, the 18th, okay.
Yeah, no class the 18th. Yes, class 25th.
Okay.
Yeah.
Thank you.
Okay, you're welcome. All right. So if that's it, then everybody have a great week, and I'll see you in 2 weeks.
You too.
Okay, bye.